Hello. Well, this is the last lecture, so I'm going to get started. The first thing I want to do is I want to finish. I didn't get finished last time. That should take about 15 to 20 minutes. And then I'm going to let you ask any questions you have from studying for the quiz. I know that some of you was asking if you have done well on all previous quizzes and the one with the lowest grade will be dropped. Is it okay to not take today's quiz? Absolutely. If you feel like this quiz, whether you do well or not do well, is not going to affect your overall grade, there's no need to take it as long as all your previous quizzes have done very well. But if you feel like one of your past quizzes wasn't very high and that you want to improve your quiz grade, you should try to do really well on this one so that the lower grade from the past will be dropped. So yeah, so if you don't feel like you need improvement on the quiz grade, you don't have to take it. It's not like you have to. There's no penalty in not taking this one. Your quiz grade will be calculated from all previous 5 quizzes in that case. All right. So let me finish what I didn't get to finish yesterday, and then I'm going to let you ask questions. So recall that last time we talked about a couple of things. I'm going to write down them again, and because we need them. So the first thing I'm going to write down is a Taylor's inequality. Which says if the absolute value of the n+1's derivative, so that's a derivative, of f of x is less than or equal to m. So let me note this is n+1's derivative of f of x. If that's less than or equal to m, then the error that we can the error of approximation of nth degree polynomial approximation, note r sub n of x in an absolute value will be less than or equal to capital M over n+1 factorial times absolute value x minus a absolute value to the n+1 for x minus a absolute value is less than or equal to some constant d. We're going to talk about what the d should be. So that's the Taylor's inequality. The next thing we talk about was the exercise e to f of x equals e to the x. And then we talk about the Maclaurin series expansion or the Taylor series expansion at a equals 0. So that's a sigma n equals 0 to infinity x to the n over n factorial. This is a equals 0, or you can think about x equals 0. And then we also found that the 4th degree polynomial approximation for e to the x, which is sigma I from 0 to n, in this case it's 4, and then x to the I divided by I factorial. And if we expand it, that becomes a 1 plus x over 1 factorial plus x squared over 2 factorial, x to the 3rd over 3 factorial plus x to the 4th over 4 factorial. This is the 4th degree polynomial approximation. So the question is, if I'm only, so I think I draw the diagram last time. Let me just redraw this. So if this is e to the x, And this is the fourth degree polynomial approximation. It's not going to be exactly on top of each other everywhere, right? Because then they're not the same function. One is the approximation, one is the exact function. So this in the red mark is a fourth degree polynomial approximation. So the question is, if I'm only looking at from -2 to +2, so let's see, I'm just focusing on this area between in this interval I picked. So pick x to be from -2 to +2. So how accurate is this fourth degree polynomial approximation? And what is the approximation error? So that's what I'm interested in. And let me note, last time I briefly said that the error of approximation is given by this absolute value of R sub n. So this is the error of approximation. So we basically want to know how big could this be, right? What is the reasonable range for this error there? So how do we find the error? We're going to use Taylor's inequality, try to basically follow step by step, try to calculate the absolute value of R sub n of x. So we're going to use Taylor's inequality. The error of approximation is given by the absolute value of R sub n of x, and that's going to be less than or equal to m. We don't know what m is, but don't worry, just write it down for now. N plus 1 factorial x minus a to the n absolute value to the n plus 1. And it was a condition if f to the n plus 1's derivative of x absolute value is less or equal to m. We're going to use this information later to find m. And I'm going to in this case, we have the fourth degree polynomial approximation, right? So that means the error is given by the R4, so R sub 4 of x, so n equals 4 basically. That's going to less than or equal to m over 4 plus 1 factorial, 5, that's 5 factorial. Absolute value x minus a, absolute value to the 4 plus 1. So that's going to be less than or equal to m over 5 factorial x minus a to the 5th power. I hope you're with me. So all I did is all right, I'm not going to respond to anything in the chat box because I think there's a few people said it quite clearly, right? So let's just focus on this example, and then if you have further questions about the quiz that will be dropped, I can explain it again. So here are two parts that I need to find. One is m. I don't know what m is. The other part is this x minus a. I don't know what it is. If I have them, then I know how big the error is. So how do I find m? To find m, we're going to have to use this condition, the 5th derivative, the f to the n plus 1's derivative of x is less than or equal to m. So that's an important piece we're going to use. And x minus a, we can find it by using the fact that x is between 2 and a -2. That's the information we're going to use. We're going to use to find x minus a. And the m, we're going to find it using this information. So let me find them, and then I'm going to plug back into this error formula. So here the n equals 4, keep in mind. So what do we know? We know that the f to the 4 plus 1 derivative of x, which we can find, so that's equal to the 5th derivative of x. Remember that the function, so the function f of x is equal to e to the x. So what is the 5th derivative of e to the x? Well, it's e to the x, the derivative is e to the x, the derivative of that is also e to the x, and the derivative of that is also e to the x. So it doesn't matter how many derivatives you take, it's always e to the x. So that will be e to the x. What is this? We want to know the m, which is bigger than this. What is the range of e to the x? That's a question. What is the upper bound? What is the lower bound of e to the x? Well, e to the x, for x is from -2 to 2, it's going to be between e to the squared is greater or equal to e to the -2. So that's the range of e to the x. So e to the x absolute value is going to be between e squared and the e to the -2 because they're all positive, which tell us that e to the x absolute value is going to be less than or equal to e squared, which we can call this e squared, it's just m. Because m is an upper bound, that's what we want. We want to know what is the m value that the derivative, the 5th derivative, that's what I say here, the 5th derivative is going to be less than or equal to. And in this case, we found that m is going to be e squared. So we can conclude that the 5th derivative of x absolute value is less or equal to m, which is equal to e squared. So this is what the m value we're going to use. It's a e squared is the upper bound of this absolute value. So now I can shove it in there. So this is going to be less than or equal to e squared over 5 factorial absolute value x minus a to the 5th power. Now, how do we find x minus a? I said earlier, we're going to find absolute value x minus a by using -2 less or equal to x less or equal to 2. So note, x is between 2 and a -2, which means absolute value, which means if we subtract 2 from both sides, not subtract 2, which means that we can write as absolute value of x is going to be less than or equal to 2. That's what it means when we write it using inequality by expanding the absolute value. So absolute value of x is less than or equal to 2, which you can write as x is greater or equal to -2 less than or equal to 2, which you can also write as x minus 0 is going to be less than or equal to 2. And then the a there we given from the Taylor series expansion, the a is 0 because we expand the series at a equals 0. So that means this part here we can write as e squared over 5 factorial absolute value x minus 0 absolute value to the 5th power. But this absolute value part of x minus 0, this chunk we know is less than or equal to 2. So that means we can substitute 2 in there for this absolute value. So that's going to be less than or equal to e squared over 5 factorial times 2 to the 5th. And now we found the m, we found the absolute value of x minus 0, So we can just basically calculate this using a calculator. That's going to give you a number that's about 1.9704. This is the biggest error you can get in this approximation. So I don't know if this makes any sense to you. This is the sort of the technique to use. Well, one of the techniques. This one using Taylor's inequality used to estimate the approximation error. So the error could be any number, could be 1, could be 1.2, could be 0.5. It's going to be less than or equal to 1.9704. All right, there's a couple questions asking, is this going to be on the quiz? No, it's not going to be on the quiz. But it's good to know because you might have to apply this in your, if you take calculus 3, I think that's multivariable calculus, you might end up using this information. Or if you take differential equations, excuse me, you might end up using it. So it's good to pay attention to those, even though it's, you know, you don't have homework on this, you don't have assessments on them, but it's good to know. So this is the error at the end, 1.97, which it's actually pretty big error considering that, you know, you talk about function e to the x, right? So the error here, it's actually a lot larger because e squared, so e to the x, go back to the graph I had. So e to the x, when x equals 2 is e squared. It's less than 9, right? It's less than 3 squared. So if you already, so the actual value is less than 9, but if you already have an error that's going to be almost 2 units, so the approximation going to be 2 units away from 9. So that's a very large error when you compare to the actual y value. So the approximation is not great. But if we change the interval from -1 to 1, the error will be a lot smaller. All right, I'm going to go through another example on this really quickly. Again, this is the last thing we talk about. I do want to kind of go through this, make sure you kind of see, even if you don't understand every part of it, but at least to see what is going on. All right, the next exercise is that we're going to approximate f of x equals square root of x, that's just a 2 square root of x, by a Taylor's approximation, Taylor polynomial, just basically means the Taylor series approximation. Polynomial of degree 2 at x equals 4. So basically what this says is that we're going to find the Taylor series, but we only want the first 3 terms because the degree is 2. The process to do this is just the same thing as you always do with Taylor series expansion. So I'm going to just make a list. Since I've done the work already, I'm just going to write them down. Square root of x equals x to the half. The first derivative, if you take it, you end up with 1/2 and the square root of x in the denominator. The second derivative, it's going to be -1/4 with cube of square root of x in the denominator. And then the third derivative, which we don't need in this part, but we will need it later, that's going to be let's see, positive 3/8 with square root of x in the 5th power. So you can try this on your own, but just to save time. So those are the values that we would possibly need. Those are the derivatives, not values. And then if we put in the x equals 4 or a equals 4, doesn't matter how you look at it. F of 4 gonna give us 2. F prime of 4 give us a 1/4. F double derivative of 4 give us negative 1/32. And then the next one, I didn't calculate it, but for now, let's just leave it for the way it is. The second degree polynomial approximation, T2 of x, there will be just the first 3 terms of Taylor series. That will be 2 plus 1/4 over 1 factorial times x minus 4. And then the next term will be plus negative 1/32 over 2 factorial x minus 4 squared. So that's a second degree polynomial approximation. The question, so that's the first part. The second part is how so if we consider x is from, let's see, we consider x is from 3 to 5. How accurate is this approximation? So I'm going to draw a diagram quickly. So the function is square root of x. So we know square root of x looks like this. Let's see, 4 is here. The approximation, I don't know what it looks like exactly, but let's just say the approximation looks perhaps is something like this. This is the second degree polynomial approximation. Did I write it correctly? It's a quadratic, so it's probably going to look something like this. Excuse me. So I'm just estimating what it looks like. It may not be accurate. You kind of have to plot it. So we want to know from 3 to 5 in this interval, what is the arrow? So what is this arrow here? Or on this side, what is the arrow? Or anywhere between, what is the arrow between the approximation, the red curve, and also the given function square root of x? What is the maximum error? What is the possible range for error, right? So that's what we're interested in. We're going to use Taylor's inequality to find it. We're going to have, we know that the n equals 2 because we talk about second degree polynomial approximation. So R2 of x, absolute value, that's going to be less than or equal to some constant m divided by 2 plus 1 factorial. It's just n plus 1 factorial if we follow the Taylor's inequality definition. It's this expression, that's the one that I'm copying down now, with n equals 2. And the times x minus a raised to the 2 plus 1's power. And again, the 2 parts we need to figure out. We need to figure out the m. We need to figure out this x minus a absolute value. Because the rest we know. We know 2 plus 1 is 3 factorial. We know 2 plus 1 is 3 in the exponent. So we need to know m. We need to know x minus a. How do we find m? So to find m, we're going to use the fact that f to the n plus 1's derivative of x is less than or equal to m. to find the upper bound by using this part. And in this case, n equals 2, so the third derivative of x, that's what we're going to use. Third derivative of f, not x. So we know that f to the third derivative of f is equal to, I found the third derivative earlier. I didn't use them, but I just found it over here. So the third derivative. So I'm going to use that. That's equal to absolute value of 3/8 square root of x to the 5th power in the denominator. How big is this? That's a question. What is the number that is less than 2? Less than or equal to, right? That's what we want to know because that's what m is. Well, we don't know that, but I know, so we know x is from 3 to 5. So we can plug in 3, we can plug in 4, we can plug in 5 and see how the value changes. So for x is between 3 and 5, 3/8 square root of x to the 5th power is going to be less than or greater than 2 values. It turns out that because square root of x is in the denominator, so we want the smallest possible value to go into x to give us the biggest output, right? Because it's in the denominator. The smallest denominator gives us the biggest quotient. So that has the maximum value given by when x equals 3. So that's a 3/8 square root of 3 to the 5th power. So this is the maximum value. The smallest value is when x is the biggest. So that will be 3/8 square root of 5 to the 5th power. So this is the smallest when x is the biggest. This is the biggest when x is the smallest. They're all positive, so it doesn't matter when you add absolute value or not. And this number is what we can use for m. So this is equal to m because it's the biggest value for this. So the third derivative, it's always going to be less than or equal to this number that I highlight in green. And in this case, we're just going to take an estimate. So that will be approximately 0.024056. That's the value we're going to use for m, because that's the approximated number that's the biggest for all x from 3 to 5 in this third derivative. So now we found the m here, so that we can put into this inequality for the error there. So remember that this gives us the error that we are interested in. So that will be less or equal to m, 0.024056 over denominator is 3 factorial, but we still have to figure out this right side, x minus a absolute value to the third power. How do we find out x minus a? We have to figure out this part, not done yet. Well, that part, just like before, we use the interval of x. So to find x minus a absolute value, we're going to use the fact that x given is from 3 to 5. So how do we do that? Well, x is from 3 to 5. We know that a equals 4, right? The very beginning, we know that the function, the polynomial approximation is centered at a equals 4. That's given. That's also the Taylor series expansion is expanded at 4. So that's sort of very useful hint. So we're going to use x between 3 and 5. So x minus 4 is going to be between -1 and 1 if we subtract 4 from all 3 terms, which tell us that x minus 4 absolute value is going to be less than or equal to 1. And then that's what x minus 4 is. So that's x minus a. So now I'm going to go to the inequality. I'm going to write as 0.0240256 over 3 factorial times x minus 4, absolute value 3. But I know that x minus 4 absolute value is less than or equal to 1. So I can substitute 1 in there for x minus 4 absolute value. So that's less or equal to 0.024056 over 3 factorial times 1. So 1 substitute for this this absolute value is less than or equal to 1. So we're going to put 1 there for this absolute value of x minus 4 cubed. Stays the same. So now if we use this to calculate it in the calculator, we get a number that's approximately 0.00402. So this is the error. So the error that of the approximation is going to be always less than or equal to 0.00402 if we look at x from 3 to 5. So go back to the diagram. So square root of x looks like this. The approximation, I don't know, I'm just drawing it, probably not accurate. This is, I don't know what that is, probably close to 4 somewhere there. And this 3 is here, 5 is here. So this error, by using this second degree polynomial approximation, this error is so small compared to the function square root of x. This error is only about 0.00402. And the y value, the actual y value is square root of 5. If you know how big square root of 5 is, right? Square root of 5 is more than 2. So if you take a number more than 2, let's say 2.1. And the approximation will give you, so let's just say the actual y value is 2.1. The error is about 0.0402. So the approximation probably give you a number that's about 2.10402. That's actually a pretty close approximation to the actual value. I'm not saying it's exactly 2.1. I'm just, guessing, right? So in this case, the error is really small, so the approximation is actually very good, relatively speaking. But if you say, oh, what if we look at x from 2 to 6, right? If you look at from 2 to 6, then it will be a little bit different. So if x is from 2 to 6, then x minus 4 will be from -2 to +2, and the x minus 4 absolute value will be less than or equal to 2. Then when you put it for x minus 2, put for x minus 4 absolute value into the error, you get the error is at some point it's equal to R2x absolute value. It's going to be less than or equal to, let's say I'm going to copy down the numbers. That'll be 0.024056 divided by 3 factorial times 2 cubed. You're going to end up with a much larger error because 2 cubed is much bigger than 1 cubed, right? 1 cubed is 1, 2 cubed is 8. So the error is almost 8 times bigger than the previous error. So it depends on the interval you're looking at, the error will be different. So anyway, so that's the new stuff I want to talk about. I should stop here. I took more time than I needed. Sorry. Yes, this notes will be posted on, this lecture will be posted on YouTube. This notes will also be available online. That way, if you want to catch up a little bit later, you can do that. All right, so I'm going to stop there. I'm going to let you ask any questions. when I'm reading this notes. So let's see, does this affect or not affect your grade? Yes, it does. It does, but if you don't take it, then it will be the quiz that get dropped. So Chris, I missed your question. When you write the nth degree polynomial expansion, notation wise, the book use I. So over here, it use I just to distinguish that in the, so this number 4 that they use for n, they use n there. So you don't want to use n again. So it's going to from I from 0 to 4. But again, if you want to, if you put 4 in there already, and then you want to use n equals 0 to 4 and x to the n factorial, that's perfectly fine. There's nothing wrong with it. So if you have t for x is equal to 4 sigma n from 0 x to the n over n factorial, that's perfectly fine. But you want to avoid that t sub n x equals sigma n from 1 from 0 to n x to the n over n factorial. You want to avoid this notation because n is the one that's changing, but if you put the same in the top of the sigma, then you're going to reach some confusion. So that was sorry, I missed your question. Let's see. Yeah, I think Chris explained it pretty clearly, right? So about the quiz, about this final quiz, just in general, one of the 6 quiz in total will be dropped. If you feel good about your previous 5 quizzes and that you don't want to take this one, that's fine. I'm going to just repeating basically what he said. But if you had the one quiz that was bad in the past and that you can do well on this one, and the bad one will be dropped, right? The worst one will be dropped, exactly. Right, yeah, so that's okay, so let me stop this nonsense and then move on to homework. All right, Sam, go ahead. You have a homework question.
So this one is the limit as x goes to 0 of -1/2 x to the x squared plus x minus natural log 1 plus x over x cubed.
Sorry, I'm going to ask you to repeat it. -1/2
squared.
What was it?
1/2 x squared plus x minus natural log 1 plus x over x cubed.
So this one, we're going to find the limit, and if you put 0 in there directly, you get a 0 over 0, which is cannot be determined. You can try to use L'Hopital's rule. That's one way, or we can just use the trick. One example we did yesterday is that we're going to use the power series representation for this natural log, but since it's difficult to find a regular power series, we're going to have to use Taylor series or Maclaurin series. It turns out that Maclaurin series is perfect for this. because x goes to 0, so we can just take the Maclaurin series at x equals 0 and put it in here. So Maclaurin series will be perfect for this case because limit x goes to 0 corresponding to a equals 0. So what is the Maclaurin series for natural log 1 plus x? Sorry, I had to look it up in my notes because it's like you don't remember. I probably don't remember. I didn't remember that neither. So Maclaurin series for natural log 1 plus x, that's equal to sigma n from 1 to infinity, -1 to the n minus 1, x to the n over n. So we're going to take this Maclaurin series, we're going to substitute into the limit to replace natural log 1 plus x. So then limit becomes limit x goes to 0, -1 over 2x squared plus x minus sigma n from 1 to infinity, -1 to the n minus 1 x to the n over n, and that's all in the sigma, divided by x cubed. Right? And then the next step is take a few terms from the Maclaurin series, just expand it, and the sum of the terms will cancel with the terms in the numerator that's there. That's already there in the numerator. So that will be limit x goes to 0. Denominator, we still have x cubed. The numerator, we have -1/2 x squared plus x minus, I'm going to put everything in a bracket. So the first term is 1n equals 1. So 1 minus 1, 0, that's a positive. So we get x over 1. When I put 2 there in that series, so right now I'm focusing on only this part, try to expand it. Put 2 there, so I have -1 to the 2 minus 1, that's a negative. And then x squared over 2. So basically have a negative x squared over 2. And then put 3 in there, so we get -1 to the square, that's a positive, x cubed over 3, and to put 4 there. You want to write enough terms to show a difference, right? If we just stop at the first 2, then we end up with 0 divided by something, which may not be a good case. So keep going. So the next term will be negative x to the 4th over 4, positive x to the 5th over 5, minus x to the 6th over 6. And I think that's enough. That's plenty terms. So now we can simplify the numerator. So here we have a negative 1/2 negative x squared over 2, basically, minus a negative x squared over 2, right? So if you have a negative minus a negative, it becomes negative plus positive, so that cancels. And the positive x here minus a positive x, so x minus x, basically. So that cancels, right? X minus x give you 0. So now what do we have in the numerator? We have limit x goes to 0. The numerator, we have x cubed over 3 minus x to the 4 over 4 plus x to the 5 over 5. And I'm not going to write the next term. And then this is the numerator, remaining part. And then denominator, we have x cubed. So divide by x cubed. I'm going to write as times 1 over x cubed. Hopefully that's okay with you. And the rest is about distributing the 1 over x cubed into each of the term. And then we can try to take the limit after that. So we get limit x goes to 0. When I distribute 1 over x cubed, I get 1/3. The next term I get negative x over 4. The next term I get positive x squared over 5 after canceling with x cubed in the denominator. And the many terms after that, but they all have an x in the numerator. Or multiples of x, right? And now we can take the limit as x goes to 0, because if x goes to 0, this term has an x in the numerator, it will go to 0. This term also goes to 0. The following terms that I didn't write, they all go to 0 because they have x in the numerator. And all we have left is just the first term 1/3. So that will be the limit. Right. Any questions on what I did in this exercise? So whenever you have a limit as x goes to 0, that you want to use power series to find the limit, you can always use Maclaurin series, because Maclaurin series is a series expanded at x equals 0, right? So you can always use that. And I think, I don't remember, but I believe that all the questions, this is in the optional homework, I believe. So all the questions with limits, you can always, take part of it and apply Maclaurin series, and then some terms will cancel, like here, the other two terms in the numerator, they cancel. And then you divide by the denominator and then take the limit, should come up very nicely. Okay. Any other questions?
That is not the answer.
That is not the answer?
Yeah, it says that's incorrect.
Let's see, what did I do wrong? Oh, bummer. Did anyone catch my mistake? I had a big mistake here because I skipped a step. I'll give you extra credit if someone pick up my mistake here. I can tell you that the mistake is going from this step to that step. No, that's not, that I actually did that in the following step. You're supposed to distribute it. I did it in the following step. So the problem is right here, going from here to there. And I'll write down what I did. That's not correct. Just because I didn't write down that step, so it caused a problem. Ah, exactly. So Jacob is right. I'm gonna write down, make sure he got an extra point on there. I didn't distribute the negative. That's exactly what the problem is. So what happened is I was just being too lazy in the numerator, not distributing the negative, just canceling two terms and forget to distribute the negative. So the correct way should be limit x goes to 0, -1/2 x squared plus x minus x plus x squared over 2 by distributing the negative to all the terms, minus x cubed over 3 plus x to the 4th over 4 minus x to the 5th over 5 and so on. Divide by x cubed. So I didn't distribute the negative by just canceling the first two terms. They still cancel. So So the negative 1/2 x squared and the positive x squared over 2 cancel. The positive x, negative x, they still cancel, right? But then the problem is that instead of having positive x cubed of 3, I should have negative because of distributing over the negative. So there should be a negative, that should be positive, this should be a negative. And then there's negative, positive, negative, positive, and it should be a negative 1/3. If that's not right, I don't know what to say at this point, but I have to check it back later.
That one's right. Thank you.
Yeah, so like, you know, I make mistakes too. It's normal that, you know, we all make mistakes when we solve for problems, but just, again, try to be very careful, right? I should do that too. All right, any other questions? It's 7 o'clock, 7:01 on my end. If you don't have any questions, we can start the quiz early.